Okay, today we're talking about the properties of logarithms, which can be a lot of fun. They help us manipulate and rearrange our equations and see equivalencies. So let's see what the first few properties are. So our first property says log base a of a to the b is just b. That's saying, remember, the answers to logarithms are exponents. So that's saying what exponent or power do I raise a to get a to the b? Well, you would just raise it to the b power. Okay, so an application of that says log base 2 of 2 to the 6. That's asking what power do I raise 2 to get 2 to the 6? And it's just 6. The idea here is that we have a logarithmic expression with base a and an exponential expression with base a, and so they undo each other. And we just get b. Okay. So the next property set is similar, but it's going in the other direction. It says if we have an exponential expression, a raised to a power, and a logarithmic expression, log base a. So again, it's the same base, but it's saying a to the log base a of b equals b. And let's think about why that would be true. If we start by thinking about this logarithm here at the top, remember the answer to a logarithm is an exponent. So this is saying what power do we raise a to get b? And whatever that power is, we're not actually finding the answer to that. We're not actually finding the power that you raise a to get b, but it's saying whatever that power is, I'm going to raise a to that power. So I'm raising a to the power you raise a to get b, and so what do I get? I get b. Okay, again, the idea is that we have an exponential expression and a logarithmic expression with the same base, and so they undo each other and we just get b. Remember, because they're inverses of each other, they do undo each other, and so that's how we can get b. So let's see an application of that. 2 to the log base 2 of 8 is just going to be 8. The exponential and the logarithm have the same base, they undo each other, and we just get 8. 2 raised to the power, we get 2 to get 8, gets us 8. Okay, and I know that's a tough one for people to think about and understand, but it's worth spending your little time on thinking about until you've got it to where you can understand it. It's okay to memorize it. All right, now this tells us the power rule that if you're taking the log of something raised to a power, you can just bring that power out front. The log base a of m to the p equals p times the log base a of m, which makes sense because when you raise a power to a power, you multiply exponents. And the answers to logarithms are the exponents you raise something to get that power. And so we can just multiply those powers together. So here, if I want log base 2 of 4 to the 6th, I've got that power. So what can I do with it? I can bring it out front. That's 6 times log base 2 of 4. Now, we can evaluate log base 2 of 4, so we're not finished simplifying this expression. The answer to log base 2 of 4, the power we raised 2 to get 4 is just 2. So 6 times 2 is 12. Okay? And what we're saying here when we finish this expression, if I go back and look at the original problem, we're saying 2 to the 12th power would give me 4 to the 6th power. Okay, if I raise 2 to the 12th power, that number would be equivalent with 4 raised to the 6th power. The power we raised 2 to get 4 to the 6th power is 12. Okay, let's try another one. It says log base 3 of 27 to the 5th. Well, I can just bring that exponent out front, so that's going to be equivalent to 5 times log base 3 of 27. We can finish evaluating that. We know what log base 3 of 27 is, so that's 5 times. What is the power we raised 3 to get 27? That's just 3 to the 3rd power, okay? 5 times 3 is 15, so final answer is 15, okay? So looking at the original expression, what we're saying is that the power we raised 3 to get 27 to the 5th is 15. 3 to the 15th power is equal to 27 to the 5th. All right, let's try another property. Okay, now this is one of my favorite properties. I usually say it in the reverse order. I usually say the difference of logs, and the difference is the answer you get when you subtract. The difference of logs is, because the equal sign is read is, the log of their quotient. Okay, so we have something that we're dividing. Okay, the fraction bar means divide. So the difference of logs is the log of their quotient. But of course, that property works in both directions, and we'll do it in both directions in our notes today. So if we have the log of a quotient, we can split it into the difference of logs as well. So let's try that in our first example here. We've got the log of a quotient, and one thing I want to point out before we get started, the base stays the same when we're splitting it into two separate logs, and if we're combining two separate logs, they have to have the same base to combine to the log of a quotient, and it'll stay that same base. So this is log base 3 of 9 over 2, so we can split that to log base 3 of 9 minus log base 3 of 2. All of the terms that are in the denominator are going to have a minus sign in front of them. All of the terms that are in the numerator are going to be positive or have a plus sign in front of them. I say all the terms because we will do ones where there are multiple terms in the denominator or multiple terms that are being subtracted. And so that's how you know whether they belong in the numerator or denominator, whether they get a plus or a minus sign. Okay, let's finish evaluating this because we can simplify this a little more. We know what log base 3 of 9 is. What power do you raise 3 to get 9? It's to the second power, or 2. Minus log base 3 of 2. We don't know the power you raise 3 to get 2, so I'll leave that as a logarithmic expression. Final answer. Okay, so let's see if we can split that quotient again. We know that the difference of logs is the log of their quotient. So if we have the log of a quotient, we can split it to the difference of logs. As soon as I see that fraction bar, I know I'm going to have a subtraction sign. So this is the natural log of 4 because it's in the numerator minus the natural log of e. The one that's in the denominator is the one that gets the minus sign. Okay. All right. Well, we can simplify this a little bit further. Remember, natural log is log base e. I don't know what power I raise e to get 4, but I do know what power I raise e to get e. What power do we raise e to get e? That's the first power. So this is the natural log of 4 minus 1. Now, this second property is similar to the one we were just talking about. And again, I usually like to say it in the reverse order, that the sum of logs is, because the equal sign means is, the sum of logs is the log of their product. So now this is two things multiplied together. The sum of the logs is the log of their product. But it does work both directions. So if we have the log of a product, we can split it into the sum of logs. So let's try this. Again, notice that all the bases have to be the same. So they have to be the same base to combine them to a single log of a product. And if it's the log of a single product that you're splitting to the sum of logs, they will both keep that same base. So here we have log base 5 of 25a. So I can split that to log base 5 of 25 plus log base 5 of a. Now we can simplify that further because we know what the log base 5 of 25 is. What power do I raise 5 to get 25? That's the second power plus the log base 5 of a. Final answer. Okay, let's try another one of these. Now this is common log. The base isn't written, but we know that's base 10. So I can split that. It's the log of a product, so I can split it to the sum of logs. So that would be the log of 10 plus the log of b. Now, we can simplify that because we know the power we raise 10 to get 10. What's log base 10 of 10? That's just 1. 10 to the first power is 10. Plus, I don't know what power we raise 10 to get b because we don't even know what b is. So I'm just going to leave that as a log of b. Final answer. Okay, so screen's going away on me. Too many screens open. Let's try this again. It's hovering and so it's wanting to switch, so I apologize. Thanks for your patience. Okay, so let's go forward to our next screen. Use the properties of logs to write the statements as the sum or difference of logs. So this time we have a lot going on. Let's see if we can split it. I know it's going to stay base e, so it'll stay natural log. And as soon as I see that fraction bar, I know I'm going to have a minus sign. So this is going to be the natural log of x squared minus the natural log of whatever's in the denominator. So that's x plus 4. Now, we can simplify that further because this power can be brought out front. So that would be 2 times natural log of x minus natural log of x plus 4. Okay, so some of you may be wondering, when do we have to put a parentheses around what we're taking the log of and when do we not? The parentheses clarify what you're taking the log of, and so they're always okay to add, and I do think they help clarify a lot, and you'll see another example of that here in just a second. But for this, we were splitting it up into the sum or difference of logs, so we're done there. Okay, let's try this next problem. Again, this is the log of a quotient, so I know that's going to be the difference of logs. So this is going to be the natural log of x minus 4 squared. It's a positive term because it came from the numerator. Now in the denominator, I have two different terms here multiplied together. You can have a whole string of terms and you can split it into sum or differences. If you have a whole string of sum or differences, as long as they have the same base, you can combine them to a single log. So it can go in either direction. Whichever terms you have multiplied together in the denominator, they're both, or however many you have, going to have minus signs in front of them. So this is minus the natural log of x minus the natural log of x plus 3 quantity squared. Okay, so let's simplify this a little bit further. I don't want to stop quite yet because I noticed that I have these exponents, so I can bring those out front. It was important that we did split this log in the denominator, not only because it had to be split, but also because if we didn't, we would have seen that we had a problem because we would have been raising all of it times 2, and only the x plus 3 is going to get, the natural log of x plus 3 is going to get multiplied by 2 because only that part was raised to that power. So that would have been an indicator that you needed to do that differently. Okay, so this is going to be 2 times the natural log of x minus 4 minus the natural log of x minus 2 times the natural log of x plus 3. Okay, and so we split it to the sum or difference of logs. Okay, let's try some more problems. This time, we're going to take them, they are written as sums and differences, and you see we have multiple terms here, and we want to write them as a single logarithm. So we're getting to go the other direction. So we've got a minus sign. I like to just kind of preview my little problem, see what we have going on here. We have a minus sign, we have a plus sign. And this term out front, no sign's written in front of it, but we know that it's positive as well. So all of our terms that are positive are going to get multiplied together in the numerator. All of our terms that are negative are going to get multiplied together in the denominator. Notice that these are all natural logs, so they're all base e, and so it'll stay, and they have to be, or we can't combine them. They'll stay base e, so they're going to stay in a natural log. I know because I have at least one minus sign, I'm going to need a fraction bar. The terms that are positive get multiplied together in the numerator. Now I got to deal with these coefficients. I'm going to do it at the same time, so that's going to be x to the 3rd power, and that's going to go in the numerator. Okay, that 4 is going to go to be the power that we raise y to, so that y to the 4th is going to go in the denominator because it had a minus sign in front of it. And that 1/3 is the power we're going to raise z to. Because it has a positive sign in front of it, it's going to go in the numerator. So that's going to be z to the 1/3. So all the terms that are positive will be multiplied together in the numerator. All the terms that are negative will be multiplied together in the denominator. If you wanted to take 2 steps to do that, you could have, we could have, if you wanted to show an extra step. I don't think it's bad to do that in one step. That's kind of the way I would do it. But if you wanted to show an extra step, you could have said that that was the natural log we could have rather written it as the natural log of x cubed minus the natural log of y to the 4th plus the natural log of z to the 1/3. So we could have just brought all the powers back first and then written them as a single log, and then written them as the natural log of, again, with all the positive terms getting multiplied together in the numerator, x cubed z to the 1/3, and all the negative terms getting multiplied together in the denominator. So if you wanted to show an extra step, that's what you would have done. A lot of you will be able to do it in one step just like I did. Okay, let's try another one. Okay, so previewing our problem. And by the way, this one that we just did, this is one that if I had my way, I would have written an extra set of parentheses around here to clarify that this was just the natural log of x. The first time I looked at this problem, I thought it was the natural log of x minus 4, but then I realized when we didn't have a sign joining the other natural log that I wasn't reading it correctly. And that's where the parentheses help clarify what you're taking the log of. Okay, so it's just there. So I always like to add them, but it just helps clarify. So again, previewing your problem will help you see what's going on. So we do have a minus sign, so that is breaking those terms there. So again, we can think of that as the natural log, 5 times the natural log base 2 of x, minus 4 times log base 2 of x plus 1, minus 6 times log base 2 of x minus 2. Okay, so how are we feeling? Do we want to try it in one step, or do you need to see it in two? If you want to do it in 2 steps, we can. We can start by just raising everything back to those powers, so bringing those coefficients back as the powers. So you can write it as log base 2 of x to the 5th minus log base 2 of x plus 1 to the 4th minus log base 2 of x minus 2 to the 6th power. That's just bringing the powers back as exponents. But then we still have another step, and some of you can have done it in one step. Notice that we have multiple terms with minus signs, so those are going to go in the denominator. This term out front is positive. It's going to go in the numerator. They're all base 2, so we're okay to combine them to a single log. So that's going to be log base 2 of, if I have even one minus sign, I know I'm going to need the fraction bar, okay? The positive terms get multiplied together in the numerator. The negative terms get multiplied together in the denominator. So that's x plus 1 to the 4th times x minus 2 to the 6th. Okay, and there we go. Log base 2 of all of that. All right, let's see what else we have to try. Nervous my hovering is going to change screens again. There we go. All right, suppose the natural log of 4 equals a and the natural log of 5 equals b. Write the expressions in terms of a and b. And every year people like this kind of gives them a little bit of a problem. It's just like, what are we doing? What is going on? This is just a contrived activity to make you convert everything into natural log of 4 and natural log of 5. So that's all it is. It's just a contrived activity, so don't worry too much about it. So can we express natural log of 20 in terms of 4 and 5? We sure can. That would be the natural log of 20 is just 4 times 5. Okay, it's just 4 times 5. Now, if we have the log of a product, we can split that to the sum of logs. That would be the natural log of 4 plus the natural log of 5. And then, of course, they told us the natural log of 4 equals a plus the natural log of 5 equals b. So I just substitute those in there. And this is what I said. This was just a contrived practice to get us to be able to practice splitting things apart and express them in terms of a and b. Okay, so I just substituted those in there, a plus b. All right, so let's try that again. Natural log of 4 over 5. This is the log of a quotient, so I know that's going to be the difference of logs. So that'll be the natural log of 4 minus the natural log of 5. The one that was in the denominator has a minus sign. The ones in the numerator are positive. All right, the natural log of 4 equals a, so I'll substitute a in for the natural log of 4. The natural log of 5 is b, so I'll substitute b in for natural log of 5, and I get a minus b. Okay, let's try another problem. Natural log of 100. Okay, now, how am I going to express 100 in terms of 4 and 5? I would say that's just the natural log of 4 times 25. Right? It's 4 times 25. And of course, we know the natural log that 25 rather could just be written as 5 squared. Okay, so 4 quarters make $1, so that's 4 times 25 is 100, and 25 is just 5 squared. Okay, now that I've figured out how to express 100 in terms of 4 and 5, now I can convert them into A's and B's. By doing, this is the log of a product, so the log of a product is the sum of logs, so I can split that to the natural log of 4 plus the natural log of 5 squared. Then I have to use that fact that we have an exponent, so we can bring that out front. So that's just going to be the natural log of 4 plus 2 times the natural log of 5. We know the natural log of 4, they said, is just a, so I can substitute a in for the natural log of 4 plus 2 times, they told us the natural log of 5 is just b, so I can substitute b in there. So that would be a plus 2b. Okay, and let's try one more. Now here they have the natural log of 0.25, and I want to express it as either 4 or 5. So actually, you might see the 25 and think we're going to do it in terms of 5, but actually, I'm going to write it as a fraction. 0.25, I know, is just 1/4. 1/4. That's the natural log of 1/4. Okay. And then, so then that would just be the natural log of, because I want it in terms of 4, that'd be the natural log of 4 to the negative first power. That would be the natural log of 4 to the negative first power to make it a mover, to take it across the fraction bar. So then if I have that exponent, I can bring it out front. So that would be negative natural log of 4, which would just be, because we know the natural log of 4 is a, so that would just give us negative a. Okay, and again, that's just a contrived little activity to make you convert things in terms of a and b. So nothing to stress about, okay? That's just what they're asking you to do. All right, let's just see. I think we have, yes, last slide. We want to learn to use our change of base formula. Now, we used to have to use, and I say we used to, that's historically, like even predates Miss Weaver's time, and we used to have to use change of base formulas much more often, because before we had calculators that could do logs with any base, they had to use log tables. So they had charts or tables of logs in the back of math textbooks, and you could flip to them and look up log values. But because they had to preprint these specific log tables for people to use, they delineated it down. They decided on 2 main log bases that they would use: log base 10, which is the common log, and log base E, which is the natural log. And so those are the 2 charts that they would print, the common log chart tables and the natural log chart tables. And then you had to use one of those bases. So if you were using a problem and it had a different base, here in our property it's base A, you would have to convert it to either base 10 or base E so that you could then go look up your answer in the tables. So that was one of the biggest uses of changing base, was to get it in a form that you could find in your pre-printed tables. Now we have calculators that are super powerful. They can let us enter any base that we want. So it's really amazing, and you'll see us do fun stuff with that now that we have those capabilities. But we still sometimes need to do a change of base so that we can manipulate a logarithmic expression when we're solving an equation. And so it's still a property we want to use. We just don't have to use it nearly as much as they used to. Okay, so that was our little history of math from Miss Weaver. So let's see what this property says. It says if we have a log base A of m, so we're taking the log base A of m, and we want to switch to some new base B. It'll be the log with a new base B of m, what you were taking a log of, over log base B, the new base, of A, the old base. Okay, so let's look at that again. So log base A of m equals log base B of m over log base B of A. And what I think of is, I think that my base, which is down low, is what goes down low. Okay, they're both going to be with a new base, and what you were taking the log of stays in the numerator, and the old base goes down in the denominator. Is kind of how I think of it, or how I remember it. Whatever works for you, let's try using it. Now notice in this expression, it says that we can change it to base B, or we can change it to common log, which we know is base 10, or we can change it to natural log, which is base E. So you can choose, and of course B is a variable, right? So that could be any base that you wanted to change it to. We can change it to any base that we want. Whatever base we change it to, it's going to be the log of that new base of what we were taking the log of in the original expression, over the log with that new base of the old base. Okay, so let's try this. Log base 4 of 73, well, what base do we want to change it to? I'll start by changing it to common log, or log base 10. So that would be log of 73 over log of 4. Remember, when it's common log, we don't have to write the base. It's so common, we all know it's base 10, okay? But what if I'd wanted to write it as natural log? Those are the two that they most frequently had to switch to. That would just be natural log of 73 over natural log of 4. And what if I wanted to get really crazy and change it to some other base? Like what if I needed it to be log base 5? That would just be log base 5 of 73 over log base 5 of 4, our old base. Okay, so switch it to any base you want. When we're in class, I'll usually ask you what base do you want to switch it to, and we'll switch it to whatever base you want. Okay, so let's try this next one, log base 6 of 42. I usually switch to common log because it's natural log because it's the shortest to write because it just takes 2 letters, ln, which we read as natural log. So natural log of 42 over natural log of 6 will usually be the one I'll pick if they don't tell us what base to change it to. Now, this is your final answer right there. Something super important I want you to know. This absolutely 100% does not equal the natural log of 42 over 6. You cannot just say that. You can't, because remember, we know the log of a quotient is the difference of logs, and these two logs are not subtracted, so they do not become the log of a single quotient. And even worse, this does not equal the natural log of 7. You cannot cancel or simplify across the fraction bar when they are in separate logarithmic expressions. And the reason for that is that this is not 42 divided by 6. This is the power we raise e2 to get 42 and the power we raise e2 to get 6. Those numbers we don't even know off the top of our head. They may not have any common factors and definitely don't simplify, okay? So these expressions are the powers we raise e2 to get 46 and the power we raise e2 to get 6. And that's why you cannot do that. It is not the same, okay? And that's what we have for you today. Good luck on working on logarithmic properties. Hope you'll find them as much fun as I do.